Father, your word says that you created everything by speaking it into existence. We looked into the heavens ever since then and wondered, and sometimes with skepticism, sometimes with awe at how everything came to be, the stars, the planets. Lord, as we study some of this today about what is in space and what everything is made of and how stars and planets came to be, I just pray that we would have minds to understand, that things would be clear, and that we would walk away with the awe of you. We pray this in Jesus' name. All right, so today we're going to look at what's called interstellar media. So inter means one of those Greek prefix things.
Inside?
That would be more intra. Did you get the right idea? You were close, we're real close. Like an intrastate, those are the highways that are inside the state, but an interstate is the highways that go
Outside? On the outside?
between states. Yeah, okay. So intrastellar would be like what's in the star. Interstellar is like what's between stars. Is there more stuff in stars or between stars? Say between. There's just a lot more space, right? Okay. So we're going to look at between star media. Basically, what is the bulk of everything that's out there made of? What does it look like? And how do you go from a whole lot of basically nothing, by the way, largely just empty space, like one particle per like several liters, one atom per several liters of volume. How does that ever become something like a star or a planet or a rock or whatever, right? And so, not looking at this from a theological angle, looking at this from a scientific angle. Like, what are the mechanisms that draw things together? Why are there giant stars? Why are there failed stars? Why is Jupiter a planet and not a star? Why is there a comet belt? Why? Not all those questions will be answered today, but that's what we're launching into, okay? So, to do that, I'm going to show you a video, and go back to this. Let me do this. There's definitely a trend here. So we go from cold neutral. Neutral as far as like, is it ionized or is it molecular? So we go from cold neutral to warm neutral to hot ionized. Well, as we do that, if you just look neutral, neutral, ionized, that's telling you what's happening to the electrons. And we're moving towards ionized. Okay. Temperature, we're moving from negative 268 degrees Kelvin, or degrees centigrade. I'm sorry, I converted it into centigrade. Let me put it back to Kelvin, just to keep it simple. So negative 100 degrees Kelvin over to 10 degrees Kelvin, right? At this point, we're getting close to like the temperature of stars. It's getting hot. And then density. Density's doing the other thing, right? So we've got maybe 1 million particles per cubic centimeter. And we're coming from maybe 1 per 10,000. So what is that? It's 0.0001 per centimeter cubed. I can write that in. That's the trend, right? We're getting more ionized. We're definitely getting hotter. These two go together. That makes sense. But our density's going the other way, and that is counterintuitive. And yet we've seen this before. We've seen this in our corona, right? So they walked you through looking at different pictures of star formation regions, of nebula, et cetera, and they took them in different wavelengths. And so what those wavelengths are doing, they're corresponding to temperature. And so we can see things at one wavelength that is this cold, dense stuff, and another that's this warm, neutral stuff, and another that's this hot, ionized stuff, because we can, depending upon the energy that they have, they release light at different wavelengths. And so if you look at just exclusively those wavelengths, you can see things that you can't see otherwise. For instance, if you had, here's us, here's the nebula, okay? So we're looking at a nebula. Well, ostensibly all you can see is at the front, right? If there are bright stars all over the place in this nebula, let me do those in green, okay? If there are bright stars in this nebula, but there's a big thick cloud of dust here, all I'm going to see is like one bright star, right? I'm not going to see all these others. And if there's a region where stars are forming, I'm not going to see them through the nebula. Because the nebula is going to be blocking it with the gas and the dust. It will be blocking things in those wavelengths. All I'm going to see is the heat that's coming off of that gas and that dust. But if I ignore that wavelength and I start looking exclusively for the ones that correspond to these other regions, like the hot ionized, etc., then I can basically see through this. And that's what you were seeing there with those different images that they were showing you, and they were kind of layering them and combining them. You would see something in one wavelength that you couldn't see in another. We'll give you an analogy from biology. We were wrapping up plants this morning. Last class, we were talking about flowers and flower petals, and what's the function of a flower petal. And pretty quickly everybody understood, well, it's to attract pollinators. Well, how do they attract pollinators? Well, they're pretty. Okay, like a bug is just sitting there going, well, that's a 10 out of 10, and that's a 1 out of 10, and I like this fly. No. Flip the switch and look at them through UV light. And all of a sudden you see landing strips. You see where the nectar's at, like just glowing in this bright color. Regular yellow, a dandelion out there is just yellow, right? You look at it through UV light, it's not just yellow. It's sending all kinds of signals, but you have to look at it through the right light. And then you see things that were hidden to you otherwise. And it's that same idea here. We have, of all the light that is out there in the universe, we can see, I don't know what percentage of it, but it's infinitesimally small. Super teeny tiny. There's all the radio waves and on the other end, the gamma rays that we cannot see with our human eyes, but we can detect them with our instruments. And so that lets us see into, it's almost like an x-ray, right? You can't see your bones, but with an x-ray you can see your bones because they can get past your skin. It's the same idea here. You can get past what you can't see and see what's actually there. Sorry, I got all hyped up within myself, just trying to get you guys somewhat interested. Why are we talking about this at all? So ultimately we got to go, where do stars come from? How do they form? What happens to them when they're done? We've talked about the main sequence. We know that's like 90% of their life. We know that stars are composed with like 70% of hydrogen. Where did the hydrogen come from? Where's it going? Where do these other things come from? Why do we have nebula? Are nebula forming stars? Are nebula coming from stars? How do I go from a nebula to a star? How does a star exploding impact all of that? That's basically, what is it all made of, and how do the parts work? Well, it's all made of gas and dust. It's still almost all made of hydrogen. Almost all the universe is hydrogen. The only reason there's anything that's not hydrogen is because stars are fusing it into heavier and heavier stuff. Okay? That's where the dust and everything else comes from, is from stars. And it exists either in just vast emptiness, but the nessness, the stuff of it, exists in three principal forms. And so we'll kind of build on that. We'll keep going with this guy for a little bit. We'll pause again. We'll talk through. Hopefully that made a little more. I know as you're watching that, you're just like, hopefully this makes, this is the big picture, right? All this is nuts and bolts. This is the big picture. All of the, like, know this, please, okay? At least write this down if you haven't already. All the matter in the universe that's not a star, right? This is interstellar. This is between the stars. Everything that's not a star exists in three forms. Cold neutral, warm neutral, hot neutral. Refers to temperature. Neutral versus ionized refers to, does it have its electrons or does it not? Right? As it warms up, it loses its electrons. We know that. That's what's going on in the core of a star, right? That's why it's plasma. It's stripped of its electrons because there's too much energy. So, at cold neutral, you're molecular. As you heat up, you ionize. Cold molecular, or cold neutral, you're cold. As you heat up, you're hot. This is surprisingly dense this is surprisingly sparse compared to that. So, two of these trend this way, the other one trends the other way, which may be a little surprising. If you take nothing else from today, get this, okay? This is the part that we need to have right now. So I'm going to give you a minute on that, and then I'm going to hit play.
light from behind stars through the dust cloud, it preferentially absorbs and scatters the blue light of the spectrum. So we're left with the red light, and so it looks like it's making the stars red. It's not actually making the stars red, it's actually just simply removing the blue light, and so we just see the red light. And why we think about that is that compare the stars that seem very red on the edges of the cloud compared to the red stars that are outside of the cloud, right? So we're looking maybe at some deep, some very quick side, but their light would be brighter, except that it's being dimmed and the blue light is being removed. And if we look at longer wavelengths of light, meaning infrared, we can see more through it because infrared light will pass through this dust and gas. Will pass.
Do you see that difference? So when you looked at it with red light, you've got a kind of a glob, right, of, hey, we don't have any kind of stars in this area. When you looked at it through visible light, you saw some red stars, mostly on the edges, right? Definitely red. You saw one or two in the middle, and you knew, like, wow, those are got to be some super bright stars, right? But now you're looking at it through infrared, right? So this was red, or visible, and this is now infrared. Infrared has a longer wavelength, and so here you're seeing a whole lot more. It's still, you can still see that it's there. It's in the much less dense than it would appear that way. But you can see, you can see a whole lot more. If you were to look in the radio wave, I suspect you see even more still.
Pass by this dust. In fact, the wavelengths of infrared are longer than the size of the particles, and since they're longer than the size of the particles, they're not through. And now we can see it's like the dust cloud isn't even there, or at least it's ghostly. So this is a longer wavelength view by the European Southern Observatory. And finally, we can look at wavelengths of light starting from the upper left, and that's 44.044 microns, or specifically that would be 4,400 angstroms. So that's well inside the visible light, and that's on the far blue end of the spectrum. So we see that it's all gone, right? And then we look at 55.55.
So what he said here is, this is basically looking at blue light, like no blue light's passing through that, right? As we move towards red, you start to see more on the edges, and then as we get longer, we get longer and longer in wavelength as we move down here, and it always puts this stupid thing away that they do not want. So this is blue light, and now we're moving towards the red. We're getting longer in wavelength. By the time we get into here, like, wow, we're able to see a lot of stuff. Here we go.
Which is 5,500 angstroms, which is more bluish and more greenish in the visible light, but it's blocking that too. Now that we get up to 9,000 angstroms, well red, visible light red, we see that the cloud looks kind of smaller, and that's 0.90 angstroms, micrometers in the outer right. And for some bizarre reason, they decide to go around rather than back to the left. So we go down and to the right at 1.25 microns, which is then 12,500 angstroms. Very long wavelength of infrared light, or at least the beginnings of one up near red. And now the light is getting through, and we look at 1.65 micron, and it's really starting to get through by the time we get to 2.16 micron, which is 21,000 angstroms. The light's pretty much getting all the way through, and the dust cloud is not even seen by that wavelength. It just kind of passes through it. It's the same kind of way that the light is passing through because it's large wavelength, in the same way that when you take a set of, like, if you take a beach ball and roll it across a whole bunch of little pebbles, it won't see the pebbles, it'll see the light. It's like a roll, like a whole bunch of pebbles. The beach ball will roll across a thin level of pebbles. It's just smooth. But now if you try to roll a pebble across a roll of pebbles that's about the same size, it'll get bounced around as you roll it across. In the same way, the wavelengths of light, long wavelengths, like a big beach ball going across the pebbles. It just doesn't see them. It doesn't perceive them. So that's what the 2.16 micron is. But when we look at the 0.44 right above it, that's like looking at wavelengths of light that are almost the same size as the particles themselves, so they really get bounced around as they go through. And so therefore they get absorbed, and you don't see through it, you get lost. All right, so that effect is called interstellar reddening. We described that extensively. You see it's got a cloud, light goes behind it, it goes through it, and as it goes through it, this light gets scattered or absorbed, and the stellar absorption lines stay the same wavelength, but all the blue light just gets removed. And so you can still tell the stellar, type, spectral types before, but the stellar spectral type is not changed. You just lose a lot of light. So you end up with stargates red, but no, but look at the absorption lines. They're the absorption lines of a bright blue star. So the blue light is just being absorbed away. And that's called interstellar reddening or interstellar extinction. And interstellar extinction is something you see when you look at a sunset. And that reddening that you see in the sky is because the sun's light in the reason you would look at a sunset and the sun looks red is because the blue light gets scattered away from your eye, and so all you're left with is the red. And the reason that you have a blue sky during the day is because someone else has a red sunset. And that blue light in the sky is all the sunlight being scattered from the sky. Because blue light is easily scattered. And in fact, the particles in the Earth's atmosphere are about the same size as blue wavelengths of light. So the exact same process is going on in the Earth's atmosphere with respect to clouds and just the atmosphere itself. The blue light is easily scattered, and red light not so much because it's longer wavelength. And so that's why we have light blue skies, we have all the pretty rain, sunsets, all everything. So here's some really cool interstellar scattering demonstrations of Arc 68 that we were talking about a while ago extensively. But then you have really cool snake nebula, and these two are right next to each other in the sky. And this is from the Palomar Digital Sky Survey. Looking at the blue, this is a picture of the blue emulsion filter set from the Digital Sky Survey. And if we look at another one, this is another one called the Pipe Nebula, which is the Pipe Nebula. There's all sorts of wonderful darkness. And it used to be thought that these things were holes in space, or maybe there were little more stars in that direction. And in fact, people thought that this was like the edge of the galaxy, or something past that. There was nothing. And that was an early thought. Early astronomers doing photographic studies of dark nebulae like these. And they ended up just being dark nebulae, not the edge of the galaxy. And a good friend of mine who did a major set of studies, his name was Art Bach. And Art Bach was a student, thought that back in the 1950s and 1940s, he published a paper in 1947 hypothesizing that these things were actually gravitationally collapsing and in essence where stars would form. And so they're called Bach globules. And Art Bach was a friend of mine when I was a little boy. And he said, "You've got to come down to your Kid Peak and see your stars." He was this wonderful Dutchman, big old hairy eyebrows, he stuck out everywhere. He was a wonderful man. He used to like to have a bottle of scotch and yell at radio astronomers. That was one of his favorite things to do. Anyway, Bart was known as a great observational astronomer, and these globules still keep his name today as places where over-dense regions where stars are forming. And one of the more prominent globules, actually, well, it's not really a globule, it is a dark dust cloud. The Horsehead Nebula shows off this and demonstrates many aspects of the interstellar medium. It has cold areas, it has hot areas, and it has extraordinarily hot areas, as well as deep, dark, cold areas as well. So the pink glow is from hydrogen, and it's hot and heated to excitation by nearby very hot stars. But you can see that there's a dark nebula, which is the Horsehead Nebula, dead center, and there's also dark nebulae off to the side that seem to be providing some of that interstellar extinction. You can see the cloud pass around it, you can see the blocks of the background light. We also see the Flame Nebula off to the left there below one of these lights. And these stars are all part of the Orion Belt. And so if you went and looked at Orion's belt, you could actually see some of these things by you could look at some of the colored nebulae surrounding Orion's belt. Well, let's zoom in on the Horsehead Nebula itself, because it's one of the more prominent dark nebulae in the sky. It has such a studied extensively by lots of different people. And here is a picture of it by Adam Block at Mount Lemmon Sky Center at University of Arizona, which really highlights the hydrogen gas, which is interesting. You notice those wispy streamers in the background as it evaporates off. And we also have a different kind of nebula, which is a blue nebula. And in fact, it's the same stuff. It's a reflection nebula, and the light is reflecting off of it. But the Horsehead Nebula is, even if we zoom in even tighter, we see some really interesting features of these cloud-like structures that it's actually in motion. So there is, it does look turbulent. It looks like it's actually plowing upward and above and turning over. However, the size scales are on the order of light years. So this isn't moving like fast, although it is moving with some great speed, maybe tens or hundreds of kilometers per second. If not, maybe not even that fast. But I can't remember this actual study, but that might be something that's a good assignment to go look up. How fast are the clouds moving in the Horsehead Nebula? In any event, the pink hydrogen glow in the background it illuminates the Horsehead Nebula. But very recently, the Hubble Space Telescope took a look at this same object in infrared, and this is the view in the infrared that was released in 2013. And when we look at infrared imagery, we now then see the cloud of gas and dust as warm dust that's glowing in infrared. But yet the hydrogen gas doesn't glow in infrared, and all of a sudden we can see through the veil of it to see everything in the background. And now we see the Horsehead Nebula not as a horsehead, but as a turbulent cloud that's coming up out of the clouds below it, and an overdense region where things are occurring. So if we then we can then take a stronger view of it, and this is an interesting movie, a fly-through done, I believe, by Frank Summers at Space Telescope, to actually try to dimensionalize it and 3D-ize the view of the Horsehead Nebula as what it might look like if we were flying at it at, much faster than the speed of light, I can tell you, because this thing is on the order of half a light year or so in size, or light years is its size scale. We can see all sorts of little tiny red dots, and those are very tiny red dwarf stars in So what are some things that we can learn about specifically about the nature of these dust dark clouds? On the left-hand side, we see the view in optical, and the infrared view, a longer infrared view, we see some other stuff. And then if we look in radio light, which is the carbon monoxide 3-2 transition, which is a transition, I believe, either a vibrational transition or a rotational transition if the carbon monoxide happens. And it's such long wavelengths that it only emits those things and these are tiny forms with maybe even much more exotic sorts of things, which are hydrogen, carbon monoxide, smaller.
You look at a nebula. Just pretty generic term for gas and dust in space, interstellar media. Generally, okay, so a nebula, interstellar media. Synonymous with nebula. Nebula, you've heard the word nebulous before, right? It's no distinct shape, it's moving, it's, okay? So, interstellar media consists of, we got cold, we got medium, we got hot, right? Stuff is molecular, ionic. This is more dense than this is. When you look out at space, you see more of this than anything, including stars. Stars, though, come from this. In other ways, stars make this. As stars form, go through their life cycle. If it's a large star, it goes through its life cycle very rapidly. It will go supernova. The shock wave of that will change the shape of the nebula around it. They're massive. Just when he was showing that Horsehead Nebula, right? That was a little portion of a huge nebula. And he's saying that that Horsehead Nebula was on the magnitude of several light years across. So things could be moving at like thousands of kilometers per hour, but you can't tell. Because it's moving over such a vast area that would be indiscernible for you. All right. Some of this you cannot, because certain wavelengths of light can pass through it, certain wavelengths of light cannot. So you've got to observe it through a variety of wavelengths of light. You must, if you're going to see what there is to be seen. One principle is that the longer the wavelength, the better it's going to make it through all the dust. Longer wavelengths make it through the dust better, okay? So we're talking things like infrared or radio waves. They're not going to be phased. You and I can't see them now, right? So if you look at the night sky through a telescope or whatever, and we got stars everywhere, but all of a sudden there's no stars in this space right here. It doesn't mean there's a hole in space. He said, hey, originally people were thinking that's a hole in space. That's the edge of space. It's not the hole or the edge of nothing. There's a cloud in between. And if you could just observe that at the right wavelength, you'll see that stuff come through, right? You look at it in blue, and it was a hole. You look at it in infrared, and all of a sudden, everything pops, because it's able to make it through, okay? And so that, we're talking about interstellar, but we're also, a lot of this is about how we're observing the universe around us at all, right? You can see some stuff with your naked eye, but it's very, very limited. Right, since the invention of the telescope, and especially radio telescopes and Hubble space telescopes, and now we've got the Webb's, but we can see so much more. So much more, okay? All right, that's all I got for today. I will see y'all Tuesday.